Wow, does a year pass by quickly. Last time I stood up here, we were showing you pre-models, computer-aided design models of SAFIRE, where we thought we were going to go. And tonight, we're going to show you where we've come and how we got there. So I'm not sure how fast I'll go through the presentation. I think I have, 600 slides? No. Not that many, but there's lots of colorful ones. We're going to get into some of the hardcore engineering that goes into designing a machine of this nature, and some of the questions that the team had to address for us to get where we are. So SAFIRE, stellar atmospheric function in regulation experiment. It's a test of the electric sun model. And this model, let me see here, are we going? Okay. This is the overview. Here we go. The electric sun model. I was asked back in 2011, I'm just going to give you a really quick overview for some of you that are new, by the EU and by individuals to examine this model. And what I did is I compared it to the contemporary model. And I discovered that there's a lot of disparities with the contemporary model and came to the conclusion that, at least at this time here, it's not testable. But during this, I used a statistical evaluation tool called Designs of Experiments, which you can apply to filter through hypotheses or different models to determine whether they can be tested or not. So that's really the first couple of years, and I came to the conclusion that I think that the electric universe model is based on the principle of charged plasma affecting matter of a different electrical potential. And I came to that conclusion finally after Scott Mainwaring had given me a book written by Crooks, where he had a cathode at one end of a small jar and an anode at the other end, and had rubies in the center. And when he lit it up, the rubies started to fluoresce and radiate, is what he called it, and what we call plasma discharge. But the rubies themselves were not part of the circuit. They were just in the plasma. And what it indicates is that there's certain elements that we know now do not want to climb or fall to the electrical potential of its environment. And when that happens, that's when you end up with a plasma discharge. And it was based on that that I came to the conclusion that we may be able to test this. So phase one was a proof of concept, and it was really just to see if we could shake it out and see if it worked. Can we go in and we can recreate these things, and can we introduce some instrumentation to do some measurements? Because the data and instrumentation to measure what's going on in plasmas is extremely weak. There's not much information about it, and we're going to get into that. And we did test it, and we discovered that it would work.
We adjust pressure, voltage,
So I'm going to introduce a little more helium right now,
current,
a little bit more,
and time.
and then we'll take another sample.
Time is also a key element.
You want to shut it
When the
off,
proper
we can
combination of these factors is arrived at, the plasma spontaneously ignites.
There we go. Point 4 is going down. Let's shut it off. Pumps and argon is off.
A glow discharge forms in the chamber.
So we just leave it here. It'll start climbing by itself.
Yes.
Look at the emissions coming out. Look how bright it becomes.
We adjust the various parameters to obtain a variety of plasma regimes.
Look on the surface. See the glows?
What we are observing has no clear precedent. We are seeing things we did not expect.
Look at the pressure changes. Nice. Look at the spin. Look at the spin. Yeah, look at the spin. And that was just the initial. Afterwards, we were able to control the plasma, and these are some of the plasma phenomena that we observed, and we were starting to measure. And these double layers, we ended up finding that we had 2, 3, 4, 20. These aren't discs. These are spherical discharges. Plasma has a unique characteristic where it's translucent as you look through the center of it, and it looks like it's a disc, but in fact it's not. What you're looking at actually are spheres. And then we end up looking at things that had certain types of perturbations, but what we thought and looked at the geometry here was quite remarkable with the hexagonal type of formation, and this is all moving. This is not static. Further to this, as some of you know, we saw a dark or an extremely intense ion cloud build up around the core, and this is very common for what we see happen in SAFIRE. And when it did, it would blow off into the chamber, and when that happened, it would often release power surges of over 10 million watts. Now what we did is we limited the power to 1,800 watts. Now we don't understand this, but these are the things that we are going to now investigate in phase 2, and this is what you're going to be introduced to tonight. This is kind of a panoramic shot of the lab. What you're looking at in the center there is the chamber, which can, it's about 3 cubic meters. It's about 7 feet long, and it's about 4 feet in diameter. And we're going to go and explore the engineering that went behind this, or what's behind this. This is SAFCON. Everybody in the team, we had to come up with a name. We said, well, let's call it the control room, and nobody liked that, so we said, okay, well, let's really, they came up with the name SAFCON. So this is SAFCON, and this is kind of, again, a panoramic view here. It's not complete in this picture of where the main control for gas, vacuum, data acquisition, and in real time, we get to monitor what's going on with all the systems in the chamber. Now, there are 2 things that we're going to talk about tonight. One of them is systems, which is the chamber itself, to maintain its stability so that it's a stable experimental environment. And the other is the data that we get back from the instruments like the Langmuir probe, optical spectroscopy, mass spectroscopy, and other things. So, you're not looking at the sun. This is the result of the first discharge from SAFIRE phase 2. And this is what happened. And so we believe now that it is scalable. Well, we know it's scalable. So the SAFIRE environment, we know that the plasma itself is extremely intense. We know that it's extremely hot. And one of the things that happen in a plasma discharge, one of the characteristics of a plasma is what we call radiation emissions. And radiation emissions is the thing that you feel when you walk outside and you feel the hot Phoenix sun after you've been in the shade. And those emissions in SAFIRE, they travel at the speed of light and they impinge on the surface of the chamber. Now, I didn't think that this would be a big deal when we first started out because it's such a big chamber. It weighs almost 2,000 pounds. It's stainless steel. And I found out that that actually was not the case. This is just a small graph to show you the different types of radiation, complete spectrum. You go right from what they call non-thermal, thermal, optical, broken bands, gamma rays, X-ray, and ultraviolet. The stuff that we feel predominantly are within kind of the infrared to ultraviolet range when we walk out in the sun. But SAFIRE is going to experience many of these because it's an ionizing plasma. And this is what happens to the chamber. So when this radiation hits the surface of the chamber, some of it's reflected back, but in our case, because we have a certain type of finish, a lot of this energy is absorbed into that material. And there's transmitted radiation that comes off the outside. So if you think about your engine, it's got gas burning on the inside, and you feel the heat migrating through the engine. It gets extremely hot, and so you have this thermal conductance within the material itself. So in engineering, we had to take a look at what we call potential failure modes. The melting of O-rings, is it going to get too hot? Thermal stresses on viewports, thermal expansion of materials causing stress, thermal effect on cameras, electrical discharge, erosion of materials, deposition of materials. When you have a plasma, an ionizing plasma, we watch things get vaporized. And when we say vaporized, these are like happening in seconds. So you can have something that's metal, and it's no longer there. So you got to be careful about how much energy is in this chamber, and you got to have, good control over it. So potential failure modes. What temperatures are we dealing with? How long will it take to reach these temperatures? How do we limit thermal heating in the chamber? What are the thermal limitations of the gaskets? How do we limit the thermal heating of the viewports? What are the effects of thermal expansion? Potential failure modes. And it goes on. And the list becomes endless, because once you have this radiation in here, it's like putting a very hot, let's say, tungsten light bulb inside a shoebox. And that heat and that energy's got nowhere to go, and it'll cause a fire. Molecular solubility. Well, we're using hydrogen. Well, what about the polymer hoses that we're using? Well, they're designed to handle the hydrogen. Well, what happens if the polymer hose starts to heat up? Well, it opens up the molecular structure of the polymer hose. The hydrogen starts to migrate through, and maybe you get hydrogen embrittlement, and then you break a hose. Doesn't sound like a big deal, but if you've got pressurized hydrogen moving into the chamber, and you've got a very hot anode, it might cause some consternation amongst the team. Lowell said, I said, can we expect an explosion? And he said, well, if we do, it won't be very big. Now, you have to understand with Lowell what his background is, because he used to work at Los Alamos and Lawrence Livermore Labs and nuclear weapons. So I asked him, I said, are we talking about 1 megaton or 70 megatons? Are we just going to become like cosmic dust? So we have what we call a system. It's called Open Issues and Project Tracking. And that means that every single person on the team has a responsibility to, if you think that's a problem, it's a problem unless we know that it isn't. It's broken unless we know that it's fixed. It's not going to work unless we know that it does. It's kind of you might consider it a negative approach. But in the automotive industry, we would do the same thing with your braking system on your car. As an engineer, we would say, would you be happy if your brakes worked most of the time? Or because I got accused of being a perfectionist one time, and that's the way I answered them back. And I said, well, if I'm designing a braking system, do you want them to work most of the time, 90% of the time, 99% of the time? And what I discovered is that people want their brakes to work even if the pads are gone. So we look at where a system is going to fail, and if we can eliminate the failure modes, then we have a reasonable confidence that it's going to work. So there are thousands of issues. And each person on the team is assigned, they're a champion. We identify what the task or the issue is. The team discusses it amongst ourselves. We come up with a recommendation. The person can pursue it, and then come back maybe a day or two later, a week or a month, and say, okay, this is what I found, and maybe they are stuck on it. But the approach is that if any member on the team has an issue, the whole team has an issue. Because if they're stuck, we're all stuck. So we track through every single issue that we can think of. And that brings us to computational fluid dynamics. And it's a big word, and it's science and engineering that is used from designs of kettles to rockets, fighter aircraft, and it covers a wide range of things in thermodynamics. And it includes radiation emissions, that's light emissions. It means fluids as well as gases. So gases fall under the same kinds of laws and principles in our calculations as what liquids do. So CFD is it's a software solid modeler. It uses proven applied mathematical equations, algorithms to evaluate the effects of various interacting and non-interacting factors affecting fluids, gases, and materials. So think about when they design the radiator of your car. They know that as the radiator heats up, it's going to expand, and if they didn't let it expand, it's going to break, it's going to leak. So you want to understand the materials and the effects of the heat on these kinds of materials, and the same thing happens in SAFIRE. And you can do all these calculations at once with some of the most advanced solid modelers. So as I said before, at the beginning, I didn't think that thermal radiation was going to be too much of an effect because the thing weighs about 2,000 pounds. It's a lot of steel there, and I thought, okay, we can fire it up, and it's not going to be like the small bell jar. We can run it for maybe, a number of hours. but what I discovered in my initial calculations is that even at 30 kilowatts, because you need more power, it's a bigger chamber, we would get maybe half an hour out of the chamber before things started to melt. And if we allowed the chamber and the energy to go beyond that, maybe up to 80 kilowatts, or even 165 kilowatts, which it has the capability of doing, because it's a big chamber, we might get half an hour before it heats up to 500 degrees Celsius. And when you see something that's red hot, that would be in the range of around 500-600 degrees Celsius. And that's where things start to melt. And that's a big problem. You can't run an experiment. So what you're looking at here is a calculation called total heat flux. And you're going to kind of get a basic 101 engineering thing on this. And what I discovered something that the EU might find very useful on the heating of the cores of planets and moons. But this here is showing you the anode in the center of the chamber, and as time goes on, how radiation emissions impinge on the surfaces of the materials and the chamber itself. Now the core plasma, remember, the core plasma we figure is around 3,000 degrees. But the radiation is leaving at the speed of light. And it's traveling through the atmosphere in the chamber because it's in a vacuum even faster than it travels through our atmosphere on Earth. So there's nothing to slow it down. There's nothing to stop it. So the static results, that was Dr. Lowell Morgan's calculations. So he came up and he said, well, it looks like it's going to heat up to about 521 degrees Celsius. And I was coming up with numbers of around 535 degrees Celsius. Then I contacted some friends that were doing some work with NASA and some aerospace down in Carolinas, and they were saying maybe 550 degrees Celsius. So we have a problem. So what this is some of the calculations. This is just really a return graph. I'm going to show you some other more graphical representations of the results that the calculations came up with. But it meant we have a big problem. And it meant that I'd had to make a telephone call to Scott and say that if we ran the chamber, we could run it for about 10 minutes before you see kind of a melting thing on the floor. And that's the end of SAFIRE. What this is here, you have static results, which means this is going to be the maximum temperature the chamber will come to and it'll stabilize. The next, as you see right here, it's kind of migrating along. You see the graph drops down, it comes back up. That's giving us the time domain and how long it will take the chamber to heat. And we came up with approximately the same number, about 30 minutes. So then I thought, okay, well, I don't want to call Scott yet and say, it's over. So I thought, well, maybe we can cool it. So we'll wrap some water around it, okay, some hoses or whatever we need to do to see if we can cool the chamber. But as you can see here, the analysis is showing us that, well, where the hoses are, it's nice and cool, but right where the center of the chamber is, which is where the most of the heat is, it's going to be too complicated for us to get anything effective in there. And what you're looking at from the green to the red is what we call a thermal gradient. And it's too steep. You just don't do that to materials without causing a lot of stress and problems. So I'm thinking, well, how do we cool engines? What if we blew some air on it? So I started to do some analysis, and I thought, well, what if we put a fan on it and we suck the air down through a shroud along the surface? And we got some sort of laminar flow. And laminar flow falls under computational fluid dynamics, and this is the kind of math that they use to do wing design on aircraft. You know, how much laminar flow, how well will the air actually stick to the surface to lift the aircraft up, and air is a very effective way to get rid of heat. You use it in your radiators in your car. So it looked promising. And I thought, okay, what we can also work out here is the flow of air over the surfaces. So we can effectively predict how the winds or the air is going to flow over these surfaces to be more effective in cooling it. More effective, more efficient. And this is some of the thermal distribution, and it's a lot more even. So we're not getting 500 degrees now. If I can get a fan to pull air over the surface, we can bring the chamber into stability at around 100 degrees Celsius. Now that's something that we can work with. It's still going to boil water, but the worst case scenario is about 100 degrees Celsius. It's not going to melt gaskets. Yes, you could fry eggs on it, but it's workable. So then I thought, well, I need a fan. And that big blue thing is the fan that we came up with. I told Scott that, yes, we have a solution, but what I didn't tell him at the time is just how big a fan we needed. And so he thought, okay, this is good, so we're going to keep moving ahead. And the fan actually will suck about 14,000 cubic feet per minute at a pressure of about 2 inches of not 2 atmosphere, but 2 inches of water, which basically would suck the air out of this room, all the air out of this room here, out, I would say approximately 30 seconds. So keep your hands and feet in at all times, you know. I mean, that's me standing there. I don't know what I'm doing. I'm looking at something, I guess. So then we looked at the outside, and that looked good. So let's take a look at the inside, because that's where the real nasty environment is. And what we can model now very accurately is what these conditions are. And the conditions is showing you with the little arrows. It's showing you, those arrows are showing you the effects of buoyancy. So as hot air heats, it rises. And so effectively, those arrows are showing you that it's going to rise, and it's giving you a velocity. Well, how fast is the gas rising? And so this is gas. This is not radiation emissions. The radiation emissions are passing through the gas at the speed of light, but then there's the gas in the chamber, and how fast is it moving? Okay, do we have any kind of convection motion happening in here? And it's actually quite stable, if you look at it. The velocity is actually not that high. Is this moving? Yes. So what we're looking at here, I took a cross-section, and we're just kind of moving down through the chamber to the core, which is where the anode is. And it looks like a heck of a fire that's in there, and it is. But the velocities are very, very low. We're talking 0.0005 meters per second. So it means the gas is not moving very quickly, which is good for us, because it means that, you know, gravity is going to have a limited effect on the plasma discharge, if that makes any sense. Okay, the gas is very stable inside. And this is just actually looking down into the core. So this here is the effect of what's called total heat flux. It's how you can heat up a body using electricity. So I'm just going to digress here from SAFIRE just to talk about a possibility that the EU might want to consider, because in the course of doing this analysis, it occurred to me that we use this tool all the time, and it means that the center of the anode might be around, let's say, 2,500 degrees Celsius. But the surface temperature of the anode was almost 1 order of magnitude cooler. And I thought, now what is going on? Like, you know, if you're going to heat it up, it should be just kind of a uniform heat. But in the analysis, what it showed is that the radiation emissions leaving the surface of the anode are leaving it at the speed of light. But it takes a lot more time for the heat to migrate from the core through that very dense material that we call the anode. So if you think about it, you don't need gravity to heat the core of a planet or a moon, and this is a very effective mechanism to do this, and it does answer for why you could have hot cores in planets or moons that really, by now, in my opinion, if they're as old as they say they are, should be frozen rocks, and they're not. And even with bodies that are even smaller than our own moon, might have hot cores and volcanic activity. Just a consideration for the EU, but it's something that appears to me that might have some legs. So it's just another kind of a three-dimensional view of the core. It's fun doing this work because it's really pretty. This is stuff you could put on t-shirts, you know. So this again, what we're looking at is the radiation and the effects of the radiation on components like the cathodes, because we have large cathodes, and you'll see them tonight. They're 3 feet in diameter. They're very thick copper, and what we have to identify now is whether or not they're going to melt or they're going to expand, and what kind of changes can we see occur in the chamber without it going into a failure mode. And this is really what it's showing you. The green means that it's cool, the red means it's hot, and the little arrows show you the direction that the air is moving or the gas is moving in the chamber. This here is the results. So the maximum temperature that we got from the radiation is about 600 degrees Celsius for the copper, and that's well within copper's ability to handle it. It's going to get hot, but it's not going to melt. But when things heat up, they expand. And if you're holding something too rigid and it's wanting to expand, well, that's when you start to break things. So we can take the information that we've got and the results that we got from the computational fluid dynamics and read that directly into what's called finite element analysis. And that really deals with the structure, the strength of materials that's used in building buildings and cars and virtually every kind of thing that you can think of that undergoes any kind of stress. So if you take your hand on your desk tonight and you just put your fingers on the edge and you push your hand down, you're going to get what's called displacement. If you feel your muscle stretching, this is what we would call stress. So things can displace like the aircraft, like the wings on an aircraft, but the stresses are within its limits so they don't break off. And this is basically what FEA does. And you can apply thermal forces. And what this is showing us is the effects of the radiation emissions on the SAFIRE viewports. Okay, now if I was paying for this, these are SAFIRE viewports. Now if anyone knows anything about vacuum chambers, these really are not cheap viewports, okay? And you don't want to be blowing them out of your chamber because you're subjecting them to extremely high stresses. And what this is saying in effect, as long as we've got air moving over top of the surface, we can keep it cooled down to a point where we can effectively use them without blowing the viewports out of the chamber. But what about the cathode? Well, you come up with some ideas. You want a nice flat disk. The team, we all agreed that a nice flat disk would be the most effective way to do this. But you got to hold that disk up somehow. And this was the first concept. And this here, what you're looking at, is kind of a pie-shaped section out of that cathode that you'll see very soon. And what it's showing you is the stress is due to thermal forces. And you can see, how do I do this here? I'm going to use the pointer now, see if it blows up on me. Okay, you see right in this area here, the stresses are 372.9 megapascals. Now that might not mean much to most of you, but what it does say is that it's about 400% beyond what copper can handle. It means that the copper is going to, because of the expansion, due to the deformation that we see here, the cathode under these temperatures is going to grow about ½ inch. So how do we let it grow ½ an inch without, you know, the support structure breaking because it can't hold it anymore, you see. Okay, done. This is going so much better than last year. So far. Okay, so what we say, well, look, let's think of some concepts that come out of aircraft. Well, if the wings on an aircraft were stiff, actually they break off. And when you take off in a big airliner nowadays, you can see the wings moving up. If they didn't, those stresses would be so severe, they would actually crack and fracture and break off, and that's not a good thing. So what we're going to do with SAFIRE, and what we did is we want to let it grow. Let it grow. So in this case here, you know, we just put a small joint in here. I don't know how well you can see it on the big screen, but there's a joint in here. And it's going to let the cathode grow, and it's not going to put stresses on the structure in here, but the stresses that you can see here we're actually supporting the cathode are 77 megapascals, which is about 300% below what copper can handle. So we're in good shape. And I have enough experience with this to know that it's going to work, okay? Okay, done. Don't push the wrong button. Okay. So systems. Systems design and engineering. If you have a computer, you have a computer system. You have chips, and you have wires, and you have fans, and you have cooling systems within that computer. And that system itself is hooked into a network called the internet, and we have systems. And with this particular machine, we have to start breaking those systems out into something that's actually going to work for us in a laboratory. So the main control panel, data feedback and capture. This is in SAFCON. Video feedback. We need to see what's going on in the chamber. We have a couple of, we have one wide-angle camera. We've got a high-resolution video camera that you're going to see some of the results from tonight. Main data, vacuum, and controls, raceways. So we got to bring all the controls and other things across from the chamber into the control room. And the main power supply. And we have deionized water cooling system. The reason why we use deionized water is due to its resistivity. And we'll talk about that a little bit. And then, of course, you have the main chamber. So this is just a quick kind of overview of what SAFIRE was modeled and engineered to be. And the pictures you're going to see is really a replica of what has been modeled here over the course of the year. So we have the gimbal. You saw that last year in the model. You're going to see the real thing tonight. The chamber door, mass spectrometer, and remote data acquisition junction. That's kind of a, you'll see some interesting things there. Anode isolation chamber. Actually, that was Scott Mainwaring's idea. He says, Monty, he said, what if we just, because that chamber's so big, it's going to take you days to suck it down and get the vacuum that you want. If we want to change the anode out, we're going to lose 3 days every time we do that. And so we designed an isolation chamber where we can pull the anode back, close the gate valve, save the chamber, and switch out the anode. And this happened, I don't know how long it took us because we did this, maybe 20 minutes. And put a new one in and brought it back into the chamber. Recirculation pumps, air cooling, cryogenic vacuum, and a lot of other systems. What you're looking at here is the main gas and vacuum control systems. And the point of the presentation tonight is not just to show you SAFIRE and some of the results, but the effort and the amount of work involved with the whole SAFIRE team to get to what you're going to see tonight. And what you're looking at here is really the main gas and vacuum schematic. And everybody on the team contributes to this. The questions, well, where's it going to fail? What kind of gas are we using? What direction is the gas going through the valve? Is the valve designed to go one way? Is it more effective if it goes the other way? What about an emergency stop? What if Lowell's right, you know, and we need the big red button? What happens? How do we deal with that? Do we need to have nitrogen flood into the chamber to assure that, in fact, we've got a safe and secure shutdown? We would like to be on the evening news, but not for, because we've, you know, become cosmic dust. So we start to model these things up. So we take the schematic and we say, okay, well, what's this got to look like in real life? And we have new members on our team this year, Jason Lickfer, and he was my engineering manager with another company that I had. And so we start to design these systems. We take the schematic, which is really the engineering, and that's got to translate into drawings and parts and bills of materials. And with SAFIRE, we figure there's at least over 40,000 components, give or take. That doesn't even include the parts inside the computers. So this is a model. These are three-dimensional models. And we're not at the Iron Man stage where we're talking to the computer, but it's really getting quite advanced. So we can take materials like this here, we can know what the stresses are, read that data into an analysis software and determine whether or not it's strong enough, its properties. So what you're looking at is a three-dimensional model, but it understands all the mass properties of every single component that are in this model. This isn't just a rendering. This is where engineering is today. So now we're going to create drawings, things that people could actually use to buy materials and start to build. And this is just drawing of the control panel itself, the typical balloons, and then we get into things like bills of materials and all the parts and components and fittings and ferrules and nuts and bolts. And each part has to be ordered, and you have to identify a vendor, and you have to identify the lead time so we get the parts on the floor in time so we can build it. So what you're looking at here is purchasing. And I asked Jano last year if he'd be interested in helping me out in the purchasing side of things, and he's never done it before. I have a lot of experience in this, my other companies. And he thought, well, maybe it's calling the company up and say, I'd like to buy this part. Well, what he discovered was, what I didn't tell him is, there's this many pieces, and you're going to have to identify who the vendor is, the lead times, pricing, you're going to get quotes, and just follow-up, and when other part's going to hit the floor, and you really kind of have to have the view that the vendor's not really going to tell you the truth about the price or delivery, and they're not going to deliver on time, and when they do, it may not even be the right part. So this is Jano's creation. And he had worked on MRP systems, but we all agreed that that probably wasn't necessary for SAFIRE. Little did I say anything. We had a very limited budget, but it really did deserve a full-blown materials purchasing and system. There's a lot of components. So there were times that when I'd call him up and I could see his eyes were like two little black dots, but he hadn't run out the door yet, so I knew there was still hope. And he survived. Okay. So there he is. Jano is our control science data acquisition guy. He's the guy that is going to be responsible and is responsible for collecting all the data from all the different instruments and bringing them in and coalescing, you might say, and synchronizing the data from all the instruments. And so here we are in the lab, and he's probably looking at okay, is this working? Oh, too fast. Okay. So we have to wire it up. And we have to do checks, and vacuum checks, and leak tests. And then we have fabrication. Now, some say, well, the panel had to be fabricated. I didn't know how to split the presentation up into the different aspects. So, the panel did have to be fabricated, but we think about fabrication, we're thinking more in the lines of, machining and building and welding. And it's really cool to see how things are made. So when we go to fabricate things, ultimately you have to get the raw materials, and you have to get the parts, and they have to be machined, and they go on big boring mills, and you have to drill holes in them, and you have to prepare the holes for the feed-throughs and the flanges and the glass and all the different parts, and this is what it takes to just in the fabrication level. And there's a lot of parts, and they all have to fit together the first time. So what we're doing here right now, we're welding the flanges into the chamber. Or checking the welds. I'll just let the audio carry on here for a second. Canadian flag. If you have one pinhole, you no longer have a stable vacuum in your chamber. And normally when you build a machine that's complex, you're going to have vacuum leaks. And we do at this stage. We've got some work to do. We may have to go and discover that there's a pinhole someplace in one of these welds. And we'll have to come back and we'll have to, plug that weld. What do we got here? And then we take delivery. It's welded up. And this is at Venture Machine and DMI Precision. We have moved SAFIRE from a laboratory in Mississauga to another lab in Mississauga because basically we ran out of room. And this is the power supply. It's a big boy, but it's DC. We have extremely low, for the electrical people, we've got extremely low ripple, which means that the DC power is very clean, which is a requirement of the electric universe model, because nature expresses electricity in DC form, not AC, although it may be that there's responses. I'm digressing here. But we take delivery, and we're making preparations. And part of the preparations, of course, is, well, if we've got a scratch on the surface that's got a gasket, it's got to be polished out. And the surface, so this is Scott, and he offered his assistance, free of charge. And he asked me, you got a job for me? And I just had the job, and I said, here's a stone. It's a very fine stone. You see this big lip across the chamber here? Well, if you see any imperfections, see if you can pull those out, because every imperfection means that's where we're going to have a gas leak. Just to let you know, Scott, we don't have any leaks in the chamber door. And this is Leighton McMillan. He's on the team as well. He's not with us, but everything has to be cleaned with alcohol and prepared before you start putting the gaskets and the copper rings together. This here is the new anode base. What you're looking at is the bulkhead, services through the anode. Because at this time around, we want to be able to bring we want to cool the anode. Okay, we want to be able to make sure that we didn't see some of the failures that we saw in phase 1. So what you're seeing here is a heat exchanger, and we have water coming up, and we actually can, using a particular taper, we can take a new anode and shove it in there like you do in a drill press, and with a small screw, retain the anode. We know from the computational fluid dynamics, the thermodynamics, that the temperatures are going to reach about 1600 degrees Celsius. So if you've got composites that are in there, those plastics are going to melt. So we have to get that heat away. So we're starting to assemble the anode. And actually the anode base, the receiving base. Okay? And this is the anode isolation chamber with it pulled back where we can actually put the anode in. And what you're looking at here, actually, is this good? Yeah, this is the big gate valve. So right now the chamber can be in vacuum. We close this gate valve and, well, we close it first. Well, no, we pull the anode out first. We better pull the anode out first. Okay, then we close the gate valve, and then we open up the isolation chamber here so that we can get to the anode and replace it or do whatever kind of work that we want. Then we close it back up, open up the gate valve, and we can bring the anode back into the chamber, and it works pretty slick. This is a cathode. This is one cathode. There's a coffee cup, but kind of give you some scale. I didn't mean to leave the coffee cup there, but I see that it's there. And it's 3 feet in diameter, and the copper is about 3/8 of an inch thick. And the rings on the back are for support, because you get that kind of heat, as you know, with metals, it'll start to warp. So we have to have structural integrity as well. And this is the inside of SAFIRE. We have our cathodes, the anode, instrumentation ports, and we're going to be looking at some other things. And just take you for a tour. So systems. We're going to go back to systems here. And systems is how you get everything to talk and work together. Electrical, vacuum, water cooling systems. There are a lot of systems. There are primary vacuum systems, there are secondary vacuum systems, there's low vacuum and high vacuum, there is high voltage systems, medium voltage systems, and low voltage systems used for controls. There are data acquisition systems, computer numerically controlled servo systems, air cooling systems. We have more, but my slide is missing here. Yes. And their primary pneumatic systems, secondary pneumatic systems, gate valve switches, normally open, normally closed, indicators, lights, red lights, green lights, pumps, valves, sensors, burst disc, exhaust systems, compressors, gas systems, diffusing systems, gas analyzing system, and an emergency stop, big red button in case one of the systems fails. And I think that's it. So it's complex. This is the main vacuum pump, and it sucks, big time. It will take the chamber down to 10 minus 3 or 2, 3? 10 minus 2 in about 15 minutes. Okay? If anybody knows anything about vacuum pumps, this is from Orlicon. It's a particular pump. The nice thing about this pump is that, well, you have to cool with water because you've got your water cooling system, but you've got nitrogen cooling and diffusion line. What's that all about? Well, what that's about is, if you take a look at the middle, it says nitrogen cooling and diffusion line. It allows us to run hydrogen in the chamber, evacuate the hydrogen out, and it allows us to introduce nitrogen into the exhaust so that it's not dangerous. You see? So part of that is part of the mass spectrometer is measuring what the hydrogen content is in the exhaust, so we don't end up with dangerous fumes coming out the exhaust system in the chamber. Nice pump. Expensive pump. It's a really good pump. It's a dry pump, by the way. Now that's important because we don't want any hydrocarbons in the chamber other than what we want to put in there. We don't want oil bleeding back through the pump into the chamber, which we think we may have had a problem with in phase 1. So we're now going to look at the cryogenic pump. We hear the word cryogenic, and really what it means is you bring things down to a very cold temperature, just a few degrees above absolute zero, and it condenses the gas, and by doing that, we can bring the chamber pressure down even lower. Theoretically, we should be able to get it down to 10 minus 7, but I think operationally, in order for us to evacuate all the impurities that are in the chamber, because we need to do that if we're going to do good mass and optical and spectral analysis, we need to make sure the chamber's clean. And there's really not many things in the way of moving parts. It basically uses helium to bring the cryo pump down. I mean, the temperature of the pump down to a place where it condenses the gas. We have, if you can see here, part of what's going on here, we also need to measure, here we are here. Here we are. In the system, when we talk about systems, we have one, what we call a thermovac pressure sensor, because we need to monitor the pressure of this system before we actually turn it on. So this is the feedback that goes back to SAFCON. This is just one. And I'm going to move along here. We've got the cooling system, of course. And we have to make sure that the water that's going into the center of SAFIRE is deionized water. It doesn't have any minerals in it because the plasma, the anode is charged at 5,000 volts. So we can use water as long as it, oh, I see what's going on here. I'm sorry. Here we go. Good. So we have to deionize the water. And the temperatures, we need to keep them low, so we use a recirculation system because we can't afford to just be fresh water in and deionize it. Deionized water will not conduct electricity. So you can use water to cool things down as long as it doesn't have any mineral content in it. And so we have a high pressure pump and manifold system to distribute the cooled water out to the various characteristics, or you might say parts of the chamber, to keep them cool. And we have a deionizer that actually monitors the resistivity of the water as well. But this will give you an indication of the complexities of SAFIRE to make something like this work. Primary plasma measurement instruments. Well, we've covered this before. This is showing you the equipment that we have either on the floor or it's en route. So Langmuir probe, it took us about 8 months to work out with the Langmuir probe manufacturer to get the right kind of probe manufactured for SAFIRE. These probes are approximately 6 feet tall, and they're very, very sensitive. The this section in here is made of alumina, which is like a very fragile material, but it's extremely good when it comes to extremely nasty, hot environments. And of course, in the past, you've seen the optical spectrometer that we've been using to get some of the signatures that we got, and of course, the mass spectrometer itself. Where are we going here? Take you a tour. Now, the mass spec is probably one of the more important pieces of equipment in SAFIRE, because it tells us what we've got as a constituent gas inside the chamber. And it'll measure all the elements every 500 milliseconds and return that information back to us. So we know that when the chamber has got hydrogen in it, or if it's got argon or some other gas, or if we end up with some strange species, as some we indicated at last year's conference. But what we did this time is we said, well, look, we want to measure in different regions in the chamber. We want to measure right down near the anode. We want to measure the exhaust gas. And so we have a system by which, with just a flip of a switch, we can sample any area of SAFIRE at any time. And this is what goes on in SAFCON. This is what goes on in the control room. Data acquisition and systems control. Okay. And no scientific experiment would really be complete unless you had a rat's nest of wires and communication and pressure systems and pressure and data acquisition, I mean. So this is Leighton. He's building the, I guess really you might say, the nervous system of SAFIRE. And diagnostics. We have to troubleshoot. And all this information comes back to SAFCON. So we know if there's something getting into trouble. We know if we've got a pressure leak, overpressure. So the main power supply, as I said before, it has the capability of delivering 200 kilowatts now, DC, clean. We can control the voltage and we can control the current. And you'll see what happens when we didn't control the current. Okay, I think this is Joe giving me a lecture. Yano's listening intently. And this is just before we start to do the fire up of SAFIRE, which you're going to see in just a few minutes here. Now for the EU, Don Scott and I have talked back and forth a little bit about the low energy discharges. We can go from 0 up to 5,000 volts, and we can go from 0 up to 35 amps, or better, actually. But we have some work to do to get it refined. We have a lot of work to do. We just fired up SAFIRE for the first time last week. And the gimbal, as some of you know, it's a primary instrument to use to move a variety of instruments freely through the SAFIRE chamber. It's CNC computer numerically controlled. We have position accuracy to almost 1,000th of an inch, which means we can move the Langmuir probe through some of the double layers that we've seen and start to examine possibly Birkeland currents and diagnose what's actually going on there. Maybe we can get some answers as to why there is charge separation. Optical spectroscopy, Langmuir probe measurements, and other instruments can be added and put into the gimbal. And here it is here. So last year it was a model, and now you see the real thing. And this will give you an indication here. I think it should start the movie. Yes. How smoothly the gimbal works. So it's like a long needle, and we can bring the needle down into the plasma, and we can move it anywhere we want. And we can use it using a joystick, or we can pre-program different types of motions that are in there, or different motions that we can move. If we wanted to move a comet around, like say the anode itself, or we wanted to move out towards the cathode and measure at the anode at the same time. There are 2 gimbals on SAFIRE. And the patent was just filed on Friday, yesterday actually. So that's pretty cool. And this is all within the year. So we've been busy. It's pretty tall. The gimbal standing would be right now, I guess from where it's mounted, it'd probably be close to 7 feet. And now we're going to start up. Ben was kind enough to edit this next video you're going to see because there were certain things that occurred. And
we're at 7.2, right?
This is the startup of SAFIRE Phase 2.
5.6 torr. And we got a little bit of argon.
Yes.
No helium? Some helium? No helium.
Not much helium. Very little.
Okay.
But right now, yeah, it's rising. Current is rising. No, voltage is rising. And current as well. So we are in dark mode. We might have another discharge. So.
Show, man. Oh, look at it go. Nice. Nice.
Take the camera as well. The other. And the other cathode maybe as well. Wow.
Well, you know what is happening? Take the voltage down.
Yikes.
Kill it! Kill it! Kill it! Kill it.
Okay, so that was the first day. And what I had forgot was a little thing that Don Scott and a couple of us had talked about. Instead of limiting the current on the first discharge, I was limiting the voltage. Because I was thinking, okay, well, we just want to get enough voltage to get it ignited, but I should have actually limited the current. Now, what's missing out of this film here, well, actually what I should say is, what you actually saw at the very end was what we call a plasma flow discharge. And it resembles something like the Death Star out of Star Wars, okay? And what it does is an extremely intense ion discharge to wherever it's going, and it's focused. Well, what you don't know and what you didn't hear was actually the power supply was maxing out at 200 kilowatts, and the amount of energy was impinging on I thought the chamber at the time, but it was a screw this big. And what happened was you didn't see it in the video, but I started to see all this stuff flying off. Okay, and it was actually vaporizing the screw, okay? I thought it was drilling a hole in the side of the chamber. So Ben was kind enough to remove some of the colloquialisms I was using prior to him saying shut it off, because there was about 30 seconds in there that Joe, because we didn't actually have the main control actually hooked up inside SAFCON at the time. It was Joe sitting out and standing out by the power supply listening us to yell and please turn it up or down. And we're all screaming inside because we're freaking out because we thought we're just going to smoke a new hole in SAFIRE. We haven't even got it started yet. So, so day 2, we've learned a few things. We're going to see if we can control the current this time and not let it eat as much power as it would like. And so what you're going to see next is day 2.
Yeah,
600.
600? Okay. So you guys are on 100, eh? Bring it up. 9. Chamber pressure?
4.5.
Should go any second now. There it is.
I'm a little nervous now, you see.
How many amps?
Just bring it down about 3 if you would.
It's almost there.
Yeah, discharge the stem, but it's fine.
I got a solution for that.
So we have these anodes we can throw out. And that was day 2. So we thought that was pretty cool too. We thought, okay, we've got some good news, and now we can go to the conference, and then and tell everyone actually it works, which is great. And so, capabilities. Should we stop to talk now? Should we talk about capabilities? I'm going to fly through these quickly because I'm getting that, okay, I've been up here long enough, and I might be boring you guys. Are y'all good? You want me to okay. Well, because now that we've got SAFIRE fired up, the real work, hard work, science work, elucidating cause and effect starts. That's when the designs of experiments starts, and we can start to ask some of the questions that we have been longing to get some answers to for a very long time. So the capabilities, so it has the ability to form a variety of spherical plasma discharges. And what I will say now, I can't get into some of the details, but we do have full control over all aspects of the plasma discharge, according to Paschen's law. If you look into that, we can control everything now as a variable for us. Now, that's never been done before, ever. It can move instruments freely through the plasma atmosphere. It can do synchronous and simultaneous measurements. And we're down to picoseconds, by the way. So we can synchronize all the measurements that we're taking into picoseconds. That should be really important for us because as we move forward, there's certain events that happen very quickly, and we can capture those events. And we can synchronize all the rest of the instruments and do graphical overlay, and we can see the history or what was occurring in the chamber before it actually led up to that event. This is very important for us to do the kind of diagnostics that we need to. High resolution video, materials testing, material deposition, erosion test, Lamier probe analysis, optical spectroscopy, mass spectroscopy, near ultraviolet light measurements, infrared measurements, polarimetry, design of experiments methodology, and questions that we have. Why do ions and electrons not recombine in a double layer? Why does ionized hydrogen not go back to a stable hydrogen atom when it's in a double layer? What is the mechanism? What's the process? Why is it staying like this? Why are double layers in SAFIRE quasi-stable? So why do we form these spheres and they're quite stable? We don't know. We don't know why they form. We have some ideas, but we don't know the mechanisms and processes. We can recreate them because we understand what leads up to them, but we don't understand the physics. Why do we get huge energy surges over 10 megawatts? Maybe it has to do with the paper that Lowell, my name's on the paper too. I edited some of the things, but Lowell really is the master of that paper on ion electron trapping in these double layers. And this may be an answer to why the sun's photosphere is so intense. Maybe why that's why there appears to be fusion occurring in the sun's photosphere. Are we getting transformation of elements? Good question. Are we getting more energy out than in? We get asked that question all the time. We think now we may be able to answer some of these things. What does the voltage gradient look like before SAFIRE fires? We can confirm right now that there is a voltage gradient in SAFIRE in phase 2 before it actually ignites. But we can now go and measure that gradient. We may even be able to measure the voltage gradient before it actually does an intense stream plasma discharge to a particular point. This is the thing that leads up to lightning bolts. What's actually the environment around there that lightning bolt before you actually see a lightning bolt or plasma discharge. So is the voltage gradient, as an example, is it uniform throughout the chamber? We can measure these things now. X-rays, neutrons, gamma rays, and much more. And that's really it for this presentation. So we'll leave you with this. What I'm going to do right now is invite some of the, really the people that have been involved in SAFIRE, people that you don't really hear about, up to the stage, introduce you to them, and then I guess we're going to do a question and answer with just the core team. So thank you. It's been a privilege. Three, 4, 20. These aren't disks, these are spherical discharges. Plasma has a unique characteristic where it's translucent as you look through the center of it, and it looks like it's a disk, but in fact it's not. What you're looking at actually are spheres. And then we end up looking at things that had certain types of perturbations, but what we thought and looked at the geometry here was quite remarkable with the hexagonal type of formation, and this is all moving. This is not static. Further to this, as some of you know, we saw a dark or an extremely intense ion cloud build up around the core, and this is very common for what we see happen in SAFIRE. And when it did, it would blow off into the chamber, and when that happened, it would often release power surges of over 10 million watts. Now what we did is we limited the power to 1,800 watts. Now we don't understand this, but these are the things that we are going to now investigate in phase 2, and this is what you're going to be introduced to tonight. This is kind of a panoramic shot of the lab. What you're looking at in the center there is the chamber, which can, it's about 3 cubic meters. It's about 7 feet long, and it's about 4 feet in diameter. And we're going to go and explore the engineering that went behind this, or what's behind this. This is SAFCON. Everybody in the team, we had to come up with a name. We said, well, let's call it the control room. Wow, does a year pass by quickly. We, last time I stood up here, we were showing you pre-models, computer-aided design models of SAFIRE, where we thought we were going to go, and tonight we're going to show you where we've come and how we got there. So I'm not sure how fast I'll go through the presentation. I think I have, 600 slides? No. Not that many, but there's lots of colorful ones. We're going to get into some of the hardcore engineering that goes into designing a machine of this nature, and some of the questions that the team had to address for us to get where we are. So SAFIRE. Stellar atmospheric function in regulation experiment. It's a test of the electric sun model. And this model, let me see here, are we going? Okay. This is the overview. Here we go. The electric sun model. I was at, phase 1 was a proof of concept, and it was really just to see if we could shake it out and see if it worked. Can we go in and we can recreate these things, and can we introduce some instrumentation to do some measurements? Because the data and instrumentation to measure what's going on in plasmas is extremely weak. There's not much information about it, and we're going to get into that. And we did test it, and we discovered that it would work.
We adjust pressure, voltage,
So I'm going to introduce a little more helium right now.
Current.
Push a little bit more,
and time.
and then we'll take another sample.
Time
in
is
a minute.
also a key element.
You want to shut it
When the
off,
proper
then we can
combination of these factors is arrived at, the plasma spontaneously ignites.
There we go. 0.4 is going down. Let's shut it off. Pumps and argon is off.
A glow discharge forms in the chamber.
So we just leave it here. It'll start climbing by itself.
Yes.
Look at the emissions coming out. Look how bright it becomes.
We adjust the various parameters to obtain a variety of plasma regimes.
Look on the surface. See the glows?
What we are observing has no clear precedent. We are seeing things we did not expect.
Look at the pressure changes.
Nice, nice.
Look at the spin. Look at the spin. Yeah, look at the spin.
And that was just the initial. Afterwards, we were able to control the plasma, and these are some of the plasma phenomena that we observed, and we were starting to measure. And these double layers, we ended up finding that we had two. Back in 2011, I'm just going to give you a really quick overview for some of you that are new. By the EU and by individuals to examine this model. And what I did is I compared it to the contemporary model. And I discovered that there's a lot of disparities with the contemporary model, and came to the conclusion that, at least at this time here, it's not testable. But during this, I used a statistical evaluation tool called designs of experiments, which you can apply to filter through hypotheses or different models to determine whether they can be tested or not. So that's really the first couple of years, and I came to the conclusion that I think that the electric universe model is based on the principle of charged plasma affecting matter of a different electrical potential. And I came to that conclusion finally after Scott Mainwaring had given me a book written by Crooks, where he had a cathode at one end of a small jar and an anode at the other end, and had rubies in the center. And when he lit it up, the rubies started to fluoresce and radiate, is what he called it, and what we call plasma discharge. But the rubies themselves were not part of the circuit. They were just in the plasma. And what it indicates is that there's certain elements that we know now do not want to climb or fall to the electrical potential of its environment. And when that happens, that's when you end up with a plasma discharge. And it was based on that that I came to the conclusion that we may be able to test this. So, and nobody liked that, so we said, okay, well, let's really, they came up with the name SAFCON. So this is SAFCON. And this is kind of, again, a panoramic view here. It's not complete in this picture of where the main control for gas, vacuum, data acquisition, and in real time, we get to monitor what's going on with all the systems in the chamber. Now, there are two things that we're going to talk about tonight. One of them is systems, which is the chamber itself, to maintain its stability so that it's a stable experimental environment. And the other is the data that we get back from the instruments, like the Langmuir probe, optical spectroscopy, mass spectroscopy, and other things. So you're not looking at the sun. This is the result of the first discharge from SAFIRE Phase 2. And this is what happened. And so we believe now that it is scalable. Well, we know it's scalable. So the SAFIRE environment, we know that the plasma itself is extremely intense. We know that it's extremely hot. And one of the things that happen in a plasma discharge, one of the characteristics of a plasma is what we call radiation emissions. And radiation emissions is the thing that you feel when you walk outside and you feel the hot Phoenix sun after you've been in the shade. And those emissions in SAFIRE they travel at the speed of light, and they impinge on the surface of the chamber. Now, I didn't think that this would be a big deal when we first started out because it's such a big chamber. It weighs almost 2,000